The valve was set at 7:15 in the morning. James Thornhill turned the handwheel clockwise, 4 complete rotations from closed, until the brass indicator aligned with the chalk mark on the stem. He could feel the resistance ease as the gate lifted inside the body, releasing steam into the process line that fed the drying chambers 3 floors below. The hiss was immediate, familiar, the sound of pressure finding equilibrium. He wiped his hands on his apron, noted the setting in the logbook, and moved on to the next station. At 2 o'clock that afternoon, the foreman called him back. The flow had dropped, not catastrophically, not enough to shut down the line, but the drying chambers were running cooler than specification, and the product coming out was still damp. Thornhill climbed the iron staircase to the valve gallery, where steam pipes ran in parallel lines beneath the skylights, and found the valve he'd set that morning. The chalk mark had moved. Not much, perhaps a quarter turn, but the brass indicator no longer aligned. The handwheel sat in a position it had not occupied when he left it. He placed his palm against the wheel, felt the residual warmth of the steam below, and looked down the gallery. No one else was near. No one had reason to touch this valve. It controlled a single line, a known quantity, set once per shift and left alone. He turned the wheel back, 4 full rotations, aligned the indicator, made a fresh chalk mark across the stem and the bonnet, a continuous line that would break if the stem rotated. He noted the adjustment in the log and descended the stairs, aware of a faint unease he could not name. At 9 o'clock that evening, the night shift foreman found him in the tool room. The valve had moved again. The accusations began the next morning. Thornhill confronted the night crew. Someone had touched the valve, he said, had turned it back without logging the change, and now the day shift was being blamed for inconsistent settings. The night foreman, a man named Caulfield, denied it. No one on his crew had gone near that line. The chalk marks proved nothing, he said. Chalk could be redrawn. Thornhill could have moved the valve himself and invented the story to cover his own error. The argument moved from the shop floor to the supervisor's office. Logbooks were examined, time cards reviewed, but there was no evidence of malice, no pattern of interference. Only the valve, which had been set correctly and found later in a different position, with the chalk mark turned several degrees out of alignment. The supervisor made a decision. A new mark would be applied, this time with engineer's blue rather than chalk, a substance that stained metal and could not be easily wiped away or redrawn. The mark would be witnessed by both shift foremen and photographed. If it moved again, there would be proof. The mark was applied at the end of the day shift. A single clean line, drawn with a steel scribe dipped in Prussian blue, across the top of the handwheel, down the hub, and onto the bonnet casting. Caulfield and Thornhill both signed the log entry. The plant photographer documented the valve from 3 angles. 48 hours later, the line had shifted. The handwheel had rotated perhaps 30 degrees counterclockwise. The blue mark was no longer continuous. The separation was clean, undeniable, visible in the harsh light of the electric lamps that had been installed above the valve for observation. No one had been seen near the valve. The gallery was visible from the floor below, and workers on both shifts confirmed that no one had climbed the stairs during the times in question. Caulfield stood in front of the valve, staring at the broken line. He reached out, gripped the handwheel, and tried to turn it by hand. The wheel resisted. The packing gland was tight, the stem threads engaged. It would take deliberate force to move it. Not much force, but more than accident, more than wind or vibration or the settling of the building. Thornhill asked the question no one wanted to voice. If no one had turned the valve, what had? The valve was locked. A length of chain was wrapped around the handwheel and secured with a padlock. The key remained in the supervisor's office. A wooden sign was hung from the chain, painted in red letters, "Do not operate." The system was logged as under observation. Flow was regulated manually from a secondary valve downstream, an inconvenience that required an operator to make adjustments 3 times per shift. 3 days later, the chain was still in place. The padlock had not been opened, but the flow had changed again. The chalk mark on the secondary valve showed it had been adjusted to compensate, but the primary valve, the one that was chained and locked, had also moved. Not far, a few degrees, but enough that the gap in the blue mark had widened. The handwheel had turned inside the loop of chain, rotating just enough to reduce flow without breaking the lock. The superintendent was summoned. He arrived with 2 engineers from the design office, men who carried calipers and notebooks and an air of skepticism. They examined the valve, measured the clearance between the handwheel and the chain, and confirmed that the wheel had indeed rotated within the restraint. The lock was intact. The chain showed no signs of tampering. One engineer proposed that the valve had been installed incorrectly, that thermal expansion was causing the body to shift and the stem to rotate as the metal swelled. The other disagreed. Thermal expansion would push the stem outward, not turn it, and the valve had been in service for 8 months without issue. Why would it begin moving now? A guard was posted. A mechanic's apprentice, young and eager to prove himself, was assigned to sit in a chair at the base of the stairs and watch the valve throughout the night shift. He was given a whistle and a logbook. Every hour he was to climb the stairs, inspect the valve, and record his observations. If anyone approached, he was to sound the alarm. The apprentice lasted 4 nights. On the 5th morning, he reported that the valve had moved 3 times during his watch. He had heard nothing, seen nothing. The gallery had remained empty. But each time he climbed the stairs to make his inspection, the blue mark had shifted slightly further out of alignment. He described the experience as unnerving, the sense that something was happening just beyond the edge of perception in the moments between his inspections. He requested reassignment. The valve was no longer a maintenance issue. It had become a problem of control. A manual steam valve is a simple machine. The handwheel connects to a threaded stem that passes through a stuffing box and into the valve body. Turning the wheel drives the stem downward or upward, depending on the thread direction, moving a wedge-shaped gate that blocks or permits the flow of steam. When the gate is lifted, steam passes through. When the gate is lowered, flow stops. The position of the gate determines the flow rate, and the position of the handwheel determines the position of the gate. The valve should not move on its own. The threads are designed to be self-locking. The pitch of the threads, combined with friction in the packing gland, creates resistance that prevents the stem from rotating unless force is applied to the handwheel. This is not a complex mechanism. It relies on principles that have been understood for centuries. A screw thread resists motion unless torque is applied. A packed stem resists rotation unless the packing is worn or improperly adjusted. The valve in question had been inspected. The packing gland was tight. The threads showed no unusual wear. The bonnet bolts were properly torqued. By every measurable standard, the valve was in good condition and should have remained in whatever position it was set. Yet it moved. The engineers consulted the manufacturer's drawings. The valve was a standard rising stem gate valve, cast iron body, bronze trim, supplied by a reputable foundry in Pennsylvania. The thread pitch was 8 threads per inch, right-handed, a common specification. The stem diameter was 1 1/8 inches. The handwheel was 14 inches in diameter, providing sufficient mechanical advantage for an operator to open or close the valve with moderate effort. Nothing in the design suggested a vulnerability. Nothing in the installation suggested error. The valve was mounted vertically, stem pointing upward, the standard orientation for this type of service. The piping was properly supported. The valve was not subject to unusual vibration or mechanical stress. And yet, over a period of weeks, the valve had repeatedly closed itself by small increments, despite being marked, locked, and watched. The failure was not in the valve. The failure was in the assumption that the valve, once set, would remain set, that a machine designed to resist motion would not find a way, however slowly, to move. A manual steam valve is a simple machine. The handwheel connects to a threaded stem that passes through a stuffing box and into the valve body. Turning the wheel drives the stem downward or upward, depending on the thread direction, moving a wedge-shaped gate that blocks or permits the flow of steam. When the gate is lifted, steam passes through. When the gate is lowered, flow stops. The position of the gate determines the flow rate, and the position of the handwheel determines the position of the gate. The valve should not move on its own. The threads are designed to be self-locking. The pitch of the threads, combined with friction in the packing gland, creates resistance that prevents the stem from rotating unless force is applied to the handwheel. This is not a complex mechanism. It relies on principles that have been understood for centuries. A screw thread resists motion unless torque is applied. A packed stem resists rotation unless the packing is worn or improperly adjusted. The valve in question had been inspected. The packing gland was tight. The threads showed no unusual wear. The bonnet bolts were properly torqued. By every measurable standard, the valve was in good condition and should have remained in whatever position it was set. Yet it moved. The engineers consulted the manufacturer's drawings. The valve was a standard rising stem gate valve, cast iron body, bronze trim, supplied by a reputable foundry in Pennsylvania. The thread pitch was 8 threads per inch, right-handed, a common specification. The stem diameter was 1 1/8 inches. The handwheel was 14 inches in diameter, providing sufficient mechanical advantage for an operator to open or close the valve with moderate effort. Nothing in the design suggested a vulnerability. Nothing in the installation suggested error. The valve was mounted vertically, stem pointing upward, the standard orientation for this type of service. The piping was properly supported. The valve was not subject to unusual vibration or mechanical stress. And yet, over a period of weeks, the valve had repeatedly closed itself by small increments, despite being marked, locked, and watched. The failure was not in the valve. The failure was in the assumption that the valve, once set, would remain set, that a machine designed to resist motion would not find a way, however slowly, to move. The engineers began with the threads. The valve was drained, isolated, and removed from the line. It was carried to the machine shop and disassembled on a workbench under electric light. The stem was withdrawn from the bonnet, and the threads were examined under magnification. The thread flanks were smooth, showing the expected polish from normal operation. But there was something else, a pattern of wear that was not symmetrical. The threads on one side of the stem showed more contact than the other. The wear was shallow, almost imperceptible, but consistent across multiple threads. It suggested that the stem had been rotating under load in one direction more than the other, that the forces acting on it were not balanced. The packing was removed and inspected. The graphite-impregnated flax was compressed, but intact, showing no signs of deterioration. But the packing gland itself showed faint scoring on the interior surface, fine parallel lines that indicated the stem had been turning slowly and repeatedly within the packing. One of the engineers placed the stem in a lathe and measured its straightness. The stem was true within 0.02 of an inch, well within tolerance. But when he mounted the stem vertically in a fixture and applied a small lateral force, he noticed something. The stem wanted to rotate, not freely, but with a slight bias, as if the threads were preloaded in one direction. The other engineer fetched a thermometer and a torch. He heated the stem gently and watched the thread pitch change as the metal expanded. When he allowed it to cool, the threads contracted, but not uniformly. The thermal cycle introduced a slight torsional strain, a twisting force that accumulated over repeated heating and cooling. They began to form a hypothesis. The valve was mounted in a location where the steam temperature fluctuated throughout the day. Every time steam was admitted to the line, the valve body and stem heated. When flow was reduced or stopped, the components cooled. Each thermal cycle caused the stem to expand and contract, and because the threads were not perfectly concentric, because the packing introduced asymmetrical friction, each cycle imparted a small rotational force to the stem. But thermal cycling alone could not account for the movement. The forces were too small, the friction too great. There had to be something else, some additional mechanism that allowed the stem to overcome the resistance of the packing and rotate. They returned to the installation. and examined the piping. The steam line ran horizontally from the boiler house, rose vertically to the valve gallery, and then turned horizontal again to feed the drying chambers. The valve was located at the vertical section, with the stem pointing upward. The piping was supported by iron brackets bolted to the brick wall, and the brackets were spaced according to standard practice. But the building was old. The brickwork had settled over the years, and the floor of the gallery had developed a slight slope. The valve was no longer perfectly vertical. The deviation was small, less than 2 degrees, but enough to introduce a gravitational bias. The weight of the handwheel and stem, acting through the off-center threads, created a moment that favored rotation in one direction. And then they noticed the boiler. The boiler was a fire tube design, coal-fired, with a variable load that cycled throughout the day. When the boiler fired, the building vibrated. Not violently, but enough to transmit through the floor and into the piping. The vibration was continuous, low frequency, barely perceptible to the operators. But to a threaded stem under thermal strain and gravitational bias, the vibration was sufficient. It provided the energy to overcome friction. The reconstruction was methodical. A test valve, identical in design to the one that had been removed, was installed on a test stand in the engineering laboratory. The stand allowed the valve to be mounted at any angle and subjected to controlled vibration and thermal cycling. Instruments were attached to measure stem position, torque, and rotation. The first test was conducted with the valve mounted vertically, no vibration, no thermal cycling. The stem was set to a mid-open position and left undisturbed for 72 hours. It did not move. The second test introduced thermal cycling. Steam was admitted to the valve body for 4 hours, then shut off and allowed to cool for 4 hours. The cycle was repeated. After 48 hours, the stem had rotated approximately 5 degrees in the closing direction. The third test added vibration. A small electric motor with an eccentric weight was mounted to the test stand, producing a vibration frequency of 12 cycles per second, roughly equivalent to the vibration measured near the boiler. The thermal cycling continued. After 24 hours, the stem had rotated 15 degrees. The fourth test introduced a gravitational bias. The valve was tilted 2 degrees from vertical, matching the slope measured in the gallery. The thermal cycling and vibration continued. After 12 hours, the stem had rotated 30 degrees. The engineers documented each test with photographs and measurements. They calculated the forces acting on the stem, the thermal strain from expansion and contraction, the gravitational moment from the off-center mass, the vibrational energy from the boiler, and the asymmetrical friction in the packing gland. Each force alone was insufficient to cause movement, but combined, they created a condition in which the stem could slowly, incrementally, rotate in the closing direction. It was not a failure of the valve. It was an emergent behavior, a consequence of forces that the designers had not anticipated interacting in this particular way. The thread geometry played a role. The right-handed threads, combined with the gravitational bias, favored rotation in the closing direction. If the valve had been mounted with the stem pointing downward, the behavior might not have occurred. If the threads had been left-handed, the valve might have opened instead of closed. The vibration was critical. Without it, the friction in the packing gland would have prevented rotation. But the vibration provided enough energy to allow the stem to overcome static friction and rotate in small increments, each increment so slight that it was imperceptible in the moment but cumulative over time. The thermal cycling amplified the effect. Each heating and cooling cycle introduced a torsional strain that preloaded the threads, reducing the torque required to initiate rotation. The strain was not permanent, but it was present during the periods when the valve was most likely to move, when the system was cooling and the friction in the packing was at its lowest. The engineers prepared a report. They included calculations, test data, and recommendations for preventing similar occurrences. The primary recommendation was to install a locking mechanism on valves in similar service, a simple pin or set screw that would prevent the stem from rotating once the valve was set. The secondary recommendation was to improve the mounting, to ensure that valves were installed as close to vertical as possible and isolated from sources of vibration. But the report also included a caution. The behavior was not unique to this valve. Any valve in similar service, subject to similar conditions, could exhibit the same behavior. It was not a defect in the design. It was a consequence of the interaction between the valve and its environment, a demonstration that even simple machines could behave in unexpected ways when subjected to forces their designers had not fully considered.